9, 3, 2, 7, 8, 9.
Hello and welcome back to Calculus 1, section 3.10 on derivatives of inverse trigonometric functions. We learned a couple of sections ago the derivatives of 6 trig functions. We know derivative of sine is cosine, derivative of cosine is negative sine, and all of that good stuff. Tonight on the menu we have 6 inverse trig functions. Now these ones will be more useful for integration than derivatives. Generally we don't care about derivatives that much, but these will be back right for integration, so we need to know them to some extent. Now I'm going to list all 6 and we're going to do examples. This is a very short section because here are the formulas and we're not going to do any derivations. You can use the inverse functions and the implicit differentiation to derive these things. So if you're interested, you can do that as a practice. But since this is not an honors section, we don't have to worry about it. So here we go. The derivative of inverse sine of x is going to be 1 over square root of 1 minus x squared. The derivative of inverse tangent is 1 over 1 plus x squared. And the derivative of inverse secant is 1 over absolute x times the square root of x squared minus 1, no coughing. So these are the 3 standard ones, and now you have the 3 that will be the k. Now the interesting part for the other 3 are they're going to have the same derivatives. It's just going to be negative. So very easy to remember. The derivative on inverse cosine is just going to be negative 1 over square root of 1 minus x squared. So same, and just put the minus on top. The derivative of inverse cotangent is what?
Negative 1 over 1 plus x squared.
Perfect. And the derivative of inverse cosecant is negative 1 absolute x square root of x squared minus 1. So here are all of the inverse trig derivatives. Six. And the ones that you will use most of the time are inverse sine and inverse tangent, where inverse tangent is actually the one that will be used more than inverse sine. And as I said, they will really come to life when you start doing integration. So Calc1, chapter 5, and then you have a lot of this stuff, especially in chapter 8, Calc 2, and then differential equations later on. Will they pop up in Calc 3? Calc 3 is more like add 2 numbers and get a third number. In comparison to this joke. Cool. Now, remember how we learned chain rule? Right? So, because we learned chain rule, do we actually care about these forms? No, right? We care about inverse tangent of f of x. Because you want to have inverse tangent of e2 of x. Inverse tangent of x squared plus 1. Inverse tangent of square root of x, right? You want to have chain rule operating inside of these. Because you don't usually have vanilla functions, right? Nature is complicated. So you are going to have, most of the time, some kind of a function composition. So as you are looking at these functions, hopefully you are considering the derivative of sine inverse of f of x, so of some function in there that is plugged in. And this one now is going to be, well, the same as the previous one, except you replace every x in the answer with f of x, and then you have to multiply by the chain, which is f prime. So we are going to have 1 over square root of 1 minus f squared, and then times f prime of x. Now, instead of writing times f prime of x, you can just put f prime of x on top over here and just don't worry about it on the side. So this is actually something that you want to remember. So you know that the chain rule kicks in and you have the function on the side. Same thing happens for all other 5. So here we go with, let's say, inverse tangent, because that one is really cool and important. So if you have inverse tangent of some kind of function, it would be f prime of x divided by 1 plus f squared. Right? So that's what it is. And you know what? I am actually going to box this tangent formula here, because you are going to see this stuff actually popped up last night. This formula in terms of an integral is a backwards derivative. Last night we had the integral of e to the x divided by 1 plus e to the 2x dx. Somehow, guys, you will have to connect these two, right? And see that they are of the same form. You can see the derivative of e to dx is going to be e to dx, and you have e to dx squared, which is e to the 2x on the bottom. So this is actually the same form. Now, again, this is all the way in chapter 8, right? 8.6 is where we discussed this last night. But they had to recall this particular formula to do that problem. Otherwise, there is nothing else you can do. Well, you can type it in a computer and get the answer, obviously. But if you are faced with this on the test and you don't know this, well, that's it. And game over, right? Just write GG. So, no coughing, I said. Let's take a look at the derivative of inverse tangent of square root of x, because we can. You are using the formula above to compute this. So your f of x is root x, right? All you need to do is to plug it in where it belongs in the formula and be done with it. If you know the formula, these problems should not take longer than 1 or 2 minutes. 1 minute. 2 minutes too long. Replace your f of x with root x and then square it in the denominator, and then take the derivative of root x, plug it in the top, and then just deal with the double fraction, because we don't like double fractions. Okay, let's take a look at this together. So this is equal to 1 plus square root of x squared, because I have original f of x, which is root x. So just square it, and then take its derivative, which is 1 over 2 root x that goes on top. This works out to be 1 over 2 root x divided by 1 plus x. And if it's going to make you happy, put this over 1. So now you have double fraction. 1 times 1 is 1. And then when you multiply the two that are close by, you just get this. And that's it. That's the derivative. So you just plug in f of x in the formula where it belongs. Let's try the derivative of secant inverse of x squared plus 1. So you will first have to modify the secant inverse formula, replacing all of the x's with f of x's, and then multiplying by f prime, and then you can do the problem. So look at the formula I gave you, 1 over absolute x and blah, blah, blah. Replace all of the x's with f of x's to create the formula for chain rule. And then just plug in x squared plus 1 for f of x. So there is in blue, right there, the formula that you should be using when you replace all x's by f of x, and then you multiply by the f prime because of the chain rule. And now you will replace f with x squared plus 1, f prime with the derivative of x squared plus 1, and then simplify. Okay. So I know that my f of x is x squared plus 1. So now to solve this problem, I have this division. The derivative is just 2x. On the bottom, I have the absolute of x squared plus 1 times the square root of x squared plus 1 squared minus 1. And now we can just, fix it a little bit. So I have 2x in the numerator. And over here I can drop absolute values because x squared plus 1 is always positive. X squared makes positive numbers and then plus 1. Right? So that's going to be always positive anyway. And what I can do under the square root is I can actually square this. We don't have to do it, but let's flex a little bit. X to the 4th plus 2x squared plus 1, and then you have minus 1. So you see that you can cancel these ones, and now you can factor out x squared, which escapes the square root as x and then cancels the x in the numerator. So, it simplifies a little bit. So I have a square root. And now, under the square root, I factor out x squared, and what's left is x squared plus 2. And now this x squared jumps out, and it becomes x. And now x would cancel. and we have 2 divided by x squared plus 1 times the square root of x squared plus 2. Just a little bit of algebraic witchcraft. That's it. I hope you're not disappointed. If you are able to modify these 6 formulas when you need f of x by replacing every x you see with f of x and then multiplying by f prime, you are good to go, whether you have a basic version or chain rule version with f of x. And just make sure that you know very well inverse sine and inverse tangent, where the emphasis is on inverse tangent because it's more frequent than inverse sine. Bye.